Okay, good morning, guys. I think I just left my coffee downstairs. Wait, is that it? No, yeah, that's it. Okay, yeah, so we're good to go. Today we're going to talk more about volumes, and do it like this. Yeah. I want to start with a few problems from 6.2, kind of make sure we're feeling comfy with those, but then we're going to, come on. Yeah, we're going to switch to 6.3 and start studying the method of cylindrical shells. But first, I need some more paper. And for our last few 6.2 examples, I would be happy to work any problems that you guys wanted to work. So are there any particular problems from the homework, specifically the disk washer or slicing method problems that you guys would like to see? Yeah, what do we have here? Oh, what about Chaka? This thing. There it was. Sorry. Screen, chat. Come on up. There it is, number 3. Okay. Yeah, this is a good example of a problem. And I'm remembering now, there were a couple problems from the end of class last time that we wanted to look at also. So maybe I'll do this and then we'll take a look at that one. X equals y squared, y equals x squared, about y equals 1. About, what did I say, x equals 1? Yeah, no, y equals 1. Okay. And this is coming from section 6.2. So we should use the disk washer method or the slicing method, whichever you really prefer to call it. It really is the same thing. The trick to doing these quickly is to first draw that region that you're rotating, then to draw in a strip. Draw in a little differential thickness strip, and then imagine rotating just the strip. The solid that you get from rotating just that little differential thickness strip is the solid that we've been referring to as dV. It's the little differential volume. We come up with a formula for dV, and then we integrate dV to get V, the overall volume. So the first thing I need to do is to graph these two curves. Y equals x squared. What the hell? This is actually my vet calling me back about the cat, so I'm going to answer this call. I apologize. Hello. Hi, Kim. I'm doing good. What can I do for you?
I'm one of the emergency critical care service technicians just calling to follow up and see how Nala is doing.
So far, so good. I mean, she's still pretty lame, but when we give her the medication, she seems to perk up a little bit. Um, but yeah, definitely still in pain, still a little bit lame.
Is she using the leg?
She is. Yep, she's walking around and she's she's mobile. Limping? Yeah, she is limping.
Drinking, urinating, defecating, everything else okay?
Her appetite is definitely not what it normally is, but she is eating and drinking. Yeah. Yep. So I assume things are coming out the other end. Also, I haven't been watching the litter box too carefully. We have one other cat, so I'm not sure who's responsible for what. But yeah.
Okay. No, I understand that. Okay. I will let everyone know. Thank you so much for the opportunity to take care of Nala. We appreciate it.
Oh,
Well,
thank
have a
you.
good day and be safe.
Yeah. Okay. Thank you.
Thank you.
Bye.
Bye now.
All right. Sorry about that. So y equals x squared is this parabola, right? We know he extends over here, but I'm not going to draw that part. X equals y squared is the same as y equals the square root of x. Only when you write it as x equals y squared, normally you also think of that parabola as having more pieces over here. But again, the region that's enclosed just looks like this. So I'm not going to draw the rest of those graphs. And then the line y equals 1 is a horizontal line. Now these guys meet at the point 1, 1. And so the line y equals 1 is right here. So this is what we're going to be rotating about. Now here's the idea. The method of disks and washers, the method that we learned in section 6.2, we always draw our little differential thickness strip perpendicular to the axis of rotation. So here's my axis of rotation for disk washer. We always draw the strip perpendicular to the axis of rotation. Turns out that this is one way to characterize the method we're using, is that this is the method where your differential thickness strip is drawn perpendicular to the axis of rotation. Sure. So here is my region. My axis of rotation is that horizontal line, y equals 1. So my strip being perpendicular to it will look like this. So here's my little differential thickness strip. And I'm going to imagine rotating this strip around this line, my axis of rotation. When I do that, I will generate a little differential volume. I'll generate a little washer-shaped solid like this. That's that side, then this side. Let's see this, all right? Something like that. This is dx, it is the thickness of the strip. And I have two little radii. I have this small r, and I also have this big R. And so I need to find capital R and little r as functions of x. Because my strip is a dx thickness strip, that means I'm going to be doing a dx integral, which means I need to write dv in terms of x. Can't have any y's in it. Now, because the axis of rotation here is this line y equals 1, the formulas that you may find online or even in the textbook, unfortunately, will not work. You need to use the characterizations that I gave you in lecture last time. That little r is always the distance from the strip to the nearer end of the strip to the axis of rotation. And that big R is always the distance from the further end of the strip to the axis of rotation. So dv is pi times capital R squared minus little r squared dx, where little r is the distance from the axis of rotation to the nearer end of the strip, and cap r is the distance from the axis of rotation to the further end of the strip. All right, so these are the characterizations that we gave last time for capital R and little r. And if you come in here, you'll see that this distance right here is little r, and this distance right here is big R. All right, from the axis of rotation, which is this horizontal line, to the nearer end of the strip, which is here going to be the upper side of the strip because the axis of rotation is above the strip. And then cap R is the distance from the axis of rotation to the further end of the strip. No, you should read the textbook. I think, if I remember right, what the textbook says isn't wrong, it just doesn't work in every case. So the textbook says something like, if you're rotating about the x-axis, then you can use this formula. So it's not incorrect. And I think a lot of people do enjoy that simplicity. Maybe they don't. Some textbooks do. It depends on where you read. I know if you go Googling around, it's easy to get into trouble because many books do give an unfortunate formula. But your textbook might not commit that offense. No, it doesn't. 6.2 is good. They don't do that. But I've seen other books that do. And certainly if you're looking online, you just search, disk washer, volumes, then you'll see some formulas which are wrong. But this is okay. The textbook is good. You should always read the textbook. But then the trick is to just pay attention to what can happen when the situation changes a little bit. So we need to find big R and little r as functions of x. That's our goal. Let's look at big R first. Okay. So what is this distance? What is the distance from the line y equals 1 up here? So if I consider this as taking place at x, then this point up here on the line y equals 1 would be x comma 1. To this point down here along the graph y equals x squared. Well, that would be the point x comma x squared, right? So what is big R? What is the distance from x comma 1 to x comma x squared? Very good, yeah, 1 minus x squared, right? I take the larger guy minus the smaller guy. Up here this is 1, down here this is x squared, so this is 1 minus x squared. And little r? This is going to be a little bit tougher. I'm a little short on space, but this point right here at the top of the strip, if this is along the curve x equals y squared, that means that the square root of x is equal to y. So this is the point x comma square root of x. So the distance little r is going to be 1 minus the square root of x. It's important that we do this thing here where we solve this for y, because I need these distances to only have x's in them, cannot have any y's in them, because I'm trying to do a dx integral at the end. Are we comfy with where these r's are coming from? Big R and little r being 1 minus x squared and 1 minus root x. This is a good time to ask questions about these setups. So let me redraw this picture a little bit larger without some of the cluttering factors and see if that can help us understand where the values we have are coming from. I'm going to bring this back, but for now, just for a quick second, let me come to the side and draw this picture really big. Okay. So up here, my horizontal line, y equals 1. And then at some generic point x in this region, I imagine drawing a tiny differential thickness strip. This is the curve y equals x squared, and this other guy is the curve x equals y squared, which is the same as y equals the square root of x. If this is taking place at x, then along the bottom curve, y equals x squared, that's going to be x comma something, right? Its x coordinate is x because I'm thinking of this as occurring at a generic point there between 0 and 1. And since I'm along the curve y equals x squared, that means every point along this curve is of the form something comma that thing squared. Like if this was 1/2, it would be 1/2 comma 1/4. If it was 3/4, it would be 3/4 comma 9/16. At x, it's just x comma x squared. That's what every point along the graph y equals x squared looks like, x comma x squared. It's x comma y, where y is equal to x squared. And similarly up here, this point is x comma square root of x. Again, it's x comma y, but here y is the square root of x. So this is what it means to be on the graph y equals f of x. It's that every point is x comma f of x. So these are what two generic points along these curves look like. So then little r is always the distance from the axis of rotation to the nearer end of the strip. If I look at a generic point along this line, its coordinates are x comma y, where y is equal to 1. So it's x comma 1. So now the distance from here to here, they have the same x value, so it's just the difference of the y values. So that's 1 minus root x. And the distance over here, big R, again, they have the same x coordinate. This y coordinate is 1, this y coordinate is x squared, so big R has to be 1 minus x squared. Do we feel a little bit more comfortable with where that's coming from? So the 1 in both little r and big R is coming from the axis of rotation being y equals 1. And the key observation here, the key thing you need to get this, is that every point on the graph of f of x is of the form x comma f of x. That's the big idea. So if you take a generic point along the graph of some function, you look at x, this will be x comma f of that very same x. Like if this is 1, this would be 1 comma f of 1. All right, that's the main idea. So now back in this setting, this point along the graph y equals root x is x comma root x. This point along the graph y equals x squared is x comma x squared. So cap r is this larger distance is 1 minus x squared, and little r is this smaller distance is 1 minus root x. Which means that my dv has to be pi times 1 minus x squared all squared minus 1 minus root x all squared dx. So that's what we're going to have to integrate. And we'll be integrating it from 0 to 1, because the smallest x value in my region is 0, and the largest x value in my region is 1. I know that this is a 1 because that's where y equals x squared and y equals root x intersect. If that isn't something you happen to know off the top of your head, you would have to solve for that by setting x squared equal to root x. Questions about where this dv formula is coming from? Okay, so then I will go ahead with the integration step. Since dv is equal to that, v is equal to the integral from x equals 0 to x equals 1 of dv, which is pi, I can pop out the pi, times the integral from 0 to 1 of 1 minus x squared squared minus 1 minus root x squared dx. Now there's quite a bit of algebra that needs to be done here. We have to FOIL both of those out, combine any like terms, and then we'll be able to compute the integral. So pi times the integral from 0 to 1 of 1 minus 2x squared plus x to the 4. That's that first thing FOILed out, minus 1 minus 2 root x plus x dx. That's just multiplying out those squares or squaring out both of those binomials. Are there any like terms there? Just the constants, right? Just the constants. So we can combine those. Here I have 1 minus 1, that's 0. I'll write what's left in descending order of power, so that's x to the 4 minus 2x squared minus x plus 2 square roots of x. So when I distribute this negative and combine my like terms, that's what I get. The ones cancel. Everything else hangs out. And then this is a power rule integral. So this is pi times x to the 5 over 5 minus 2x cubed over 3 minus x squared over 2 plus, this is 2 times x to the 1/2. So 1/2 plus 1 is 3/2. So this is 2 times x to the 3/2 all divided by 3/2. And I'll just write it like that for now, evaluated from 0 to 1. Conveniently, all of these are equal to 0 when you plug in x equals 0. So I don't need to worry about any contribution from the lower limit. Also, quite conveniently, plugging in 1 doesn't require any careful computation. So this is pi times 1/5 minus 2/3 minus 1/2 plus, when I plug 1 into this expression, I get 2 divided by 3/2. That's 4/3. So that's what we get. And then we can put the bits together if we want to. Reasonable common denominator here would be 30, I guess. It's a bit of a mess. So this is pi times 6/30, right? Yeah. Minus 15/30, right? No, 15, no. What is this? So the 3 is missing a 10, so 20/30, right? 6 times 5 is 30. Yes, and so this is missing the 10, the 2 and the 5. Yeah, so multiply by 10/10, 20/30, yeah. Yep, this guy as a ratio over 30 is 15/30. And this guy as a ratio over 30 is 40/30. So this is pi times, what do we get? Minus 20 minus 15, that's minus 35. Plus 40 is plus 5. Plus 6 is 11. So this looks like 11 pi over 30. So that's the volume of this solid. This is a funky looking solid. It's kind of like a bloopy cone that's bloopy on the inside and the outside. The nice thing about the disk washer method is that we never really had to visualize the whole solid, did we? This is the general approach. This is the approach that you're going to use for most of the disk washer problems. Most of the volume problems that come from 6.2 are going to go like this. You draw on your strip perpendicular to the axis of rotation. Then you imagine rotating just that strip. That will give you your little differential solid whose dimensions you need to figure out, which means you need to find big R and little r. To find big R and little r, you think of them this way. Distance from the axis of rotation to the nearer end of the strip, distance from the axis of rotation to the further end of the strip. Each of those you need to get in terms of the variable that is the thickness of your strip, right? That is, if your strip is a dx thickness, if your strip is going up and down, so its thickness is a horizontal thickness, then you need to get big R and little r both as functions of x. If your strip happened to be a horizontal strip, then you would need you'd have a dy thickness, and you need to get both of those as functions of y. If we're having a hard time seeing why cap r and little r are what they are, you can return to this picture. The big idea is that along this curve, y equals x squared, a generic point looks like x comma x squared. So this distance right here from y equals 1 to y equals x squared is 1 minus x squared.
What about for the dV formula? How did you get pi times r squared minus r squared? Like,
well, that's the volume of a washer, right?
The volume of a washer is pi r squared.
Well, the volume of a circle, the area of a circle is pi r squared. So if I want to take something which is shaped like this, and find its volume, the way I think of this, if that's dx, and this is little r, and this is big R, The way I think of this is as a circle with a hole punched out in the middle and then given some thickness. So here's little r. If I'm looking straight on, here's little r, and here's big R. What is the area here? It's the area of the big circle minus the area of the little circle.
Pi r
Right, which is pi times cap r squared minus pi times little r squared, which is pi times cap r squared minus little r squared, factoring the pi. And then to go from the area of that thing to the volume of the washer, you just multiply by the thickness of the thing. So therefore, dV is pi times cap r squared minus little r squared times dx, because this thickness is dx. Does that make sense? No, don't stress. There's no reason to feel bad about any of this. None of this stuff is super easy. So let me look at a slightly more general example and see if we can't get comfy with that. Hamlet. Stop licking yourself, Bubba. You got hot spots on that paw. You need to stop. Sorry, I got a small zoo here. All right. So here I have just some rando function f of x. And here, let me call this line the horizontal line y equals a. If I want to find the distance from, if this is some generic point x in the domain, then the point on the line y equals a is x comma a. And the point along the graph of f of x is x comma f of x. What is this distance? Let me call that cap r. I need to take this y value, because it's the larger y value, and subtract from it this y value, right? That's this distance. It's a vertical distance, so we're going to be subtracting y values. You take the bigger y value minus the smaller y value. So here, big R would be a minus f of x. So if this curve was f of x equals x squared, and this line was y equals 1, then that would be 1 minus x squared. If this curve was y equals square root of x, and this line was y equals 1, then this would be 1 minus the square root of x. Does that help? Good, good. So what I'd like to do now is return to the problem, or one of the problems that I asked you to play with at the end of class last time. Where we want to set up an integral for the volume of the solid obtained by rotating the region bounded by y equals the natural log of x and the x-axis from x equals 1 to x equals e about the line x equals -1. So this was one of the challenge problems that I left for you guys at the end of class last time. I'll draw the picture. Here's the natural log of x. Of course, it dives off to -infinity there. E crosses the x-axis at 1. This is the point 1, comma 0. And we're asked to look from 1 to E. So this is my region. And then I want to rotate about the line x equals -1, which is this guy. So we're going to spin that region around this thing. If I'm doing this with the disk washer method, is my strip going to be oriented vertically, up and down, or horizontally, left and right?
Horizontal.
Right, because the strip needs to be perpendicular to the axis of rotation. So let me draw in a little horizontally oriented strip. That means the thickness of that strip is going to be a dy thickness. And when I spin that strip, and just that strip, around this axis, I'll get a little washer that's like laying on its side. The distances I'm going to need are the distance from the nearer end of the strip to the axis of rotation, that will be little r, and the distance from the further end of the strip to the axis of rotation. And we're going to be doing all of this at some generic, now it's a y value rather than an x value. So normally I would think of a point along the graph y equals ln x as x comma ln x. Right, just like we were saying a second ago. However, I need this point characterized in terms of y. And the trick to doing that is to solve the equation y equals ln x for x. So this is, if you exponentiate on both sides, the same as saying e to the y equals x. So this point I can think of as e to the y comma y instead of x comma ln x. And this point over here, he's along the vertical line x equals e, so he is at e comma y. They both have the same y value. They're all along this y value, so their y values are both y. Along the graph y equals ln x, the relationship between x and y is either y equals ln x, which is equivalent to saying x equals e to the y. So I have e to the y comma y. I have e comma y as my 2 points of interest, the point on the closer end of the strip to the axis of rotation and the point on the further end of the strip to the axis of rotation. And my distances here is little r, and here is big R. Nearer end of the strip to the axis of rotation, further end of the strip to the axis of rotation. Which means that little r is going to be this x value minus this x value. Now the x value at this point, you could either say is x, wouldn't be incorrect, but it's not in terms of y. And I need it to be in terms of y because my differential strip has thickness dy. So that's why we rewrote this point as e to the y comma y. So this x value here is e to the y, and the x value over here is -1, right? This is the line x equals -1. So little r is e to the y minus -1, or just e to the y plus 1. And big R, I take this x value and subtract -1 from it. Well, the x value here is just e. So this is e minus -1, or just e plus 1. The reason I like this problem so much is because I feel it's It's just the right amount of challenging. If you can get through this, then you really understand the shit. If you're having a hard time with this, then that means we need to go back and practice or fill in some sort of conceptual gap somewhere. So now is a good time to like pause and see if you're comfy with everything we've done so far. Questions about why little r and big R come out the way they do? Yeah, what do we have here? Unfortunately, the homework problems here are a little bit weak, but yes, there are problems like this. There are problems where the strip is going to be horizontal, so you'll have a dy thickness, and you'll need to recharacterize the curves from one variable to another. The last problem had this recharacterization thing where they gave us x equals y squared, and we had to write that as y equals the square root of x. Same sort of thing as what we did here. Now, there are some problems in the homework similar to this, yeah. Yeah, sure, we will go ahead and do number one. Let me finish setting up this integral. So then my little dv is pi times cap r squared minus little r squared dy, which is pi times e plus 1 squared minus e to the y plus 1 squared y. I'm not answering that right now. So the integral that we would need to evaluate here is the integral of dv, and it's going to run from the smallest y value in my region to the largest y value in my region. So the smallest y value in my region here is 0. The largest y value in my region here is 1, because I'm on the graph y equals ln x, and when x is equal to e, y is equal to the ln of e, which is 1. So this is going to be the integral from y equals 0 to y equals 1 of dv, which is the integral of 0 to 1 pi e plus 1 squared minus e to the y plus 1 squared dy. And to find that volume, you would want to FOIL those things out, combine any like terms, and then integrate. And it's not a hard integral. The hardest piece there is going to be integrating e to the 2y, which you'll get from the square of e to the y, and that's a little u sub. So I recommend going through this problem very, very carefully. Yes, Caesar just asked a really good question. How do I know if the strip is going to be vertical or horizontal? For the disk washer method, the strip is always drawn perpendicular to the axis of rotation. That's the big thing. And it turns out that's the big difference between 6.2 and 6.3, between the disk washer method and the cylindrical shell method. So if you're using the disk washer method, like here, this strip needs to be perpendicular to the axis of rotation. So here my axis of rotation is the vertical line x equals -1. Since the axis of rotation is vertical, I know my strip needs to be horizontal. That's the big thing. So for this method, disk washer method, strip is always perpendicular to the axis of rotation. Once you've drawn that in, you can kind of just follow your nose. So that is really the important thing to remember. What else are we wondering? What else feels hard or feels difficult here on this example?
When do you know to use either x or y as the bounds for the integral?
If your integral is a dy integral, so if your strip is horizontal, then you'll have to use y values for the bounds. If your strip is vertical, so your strip is a dx thickness, then you'll be using x values for your bounds. So it all comes from the strip. If the strip is horizontal, then everything needs to be in terms of y, including the bounds. If the strip is vertical, then everything needs to be in terms of x, including the bounds. What else? So that was the question that was just asked. So our bounds are always coming from the largest and smallest, either x values or y values in my region here. Since my integral is a dy integral, because my strip has a dy thickness, I know that I need to use y values for my bounds, which means I need to go from the smallest y value in my region, which is down here. The smallest y value is coming from any point along the x-axis is y equals 0, to the largest y value in my region, which is 1. So we're integrating from y equals 0 to y equals 1, because that's the smallest y value in my region, and that's the largest y value in my region. And I know to use y values because my integral is bound to be a dy integral. Okay, these are good questions. These are questions that are so much easier asked now than struggled through as you're working the homework. So what else are we thinking? Rakib, were you able to follow the argument I made there, explaining why the bounds are 0 to 1? Good, good, good. Okay, other questions here? Okay. So we wanted to look at number 1 from the homework. We'll do that, and then I'm going to introduce the method of cylindrical shells. So here we want the volume of the solid obtained by rotating the region, blah, 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 about the line. Okay. So if it's okay with you, I'm not going to write all the words. That just takes so long. This is homework 2, problem 1. We've got y equals x plus 1, y equals 0, x equals 0, x equals 7, rotated about the x-axis. So let's sketch this. Y equals x plus 1 is a line with y-intercept 1 and slope 1. Let's call this x equals 7 because I'm out of space. So here is my region, right? X equals 0, that's the y-axis. Y equals 0, that's the x-axis. So this is my region. And I want to rotate it around like this. Since I'm still in section 6.2, and I'm using the method of disks and washers, I need to draw my strip in perpendicular to the axis of rotation. This is yeah, we can look at the cone problem too. So is my strip going to be in left, right, or up, down, vertical or horizontal? Yeah, up, down, vertical, right? Because my axis of rotation is the x-axis, is a horizontal line. I'm going to draw my strip in like this. So here's my little differential thickness strip. Its thickness is dx. And on this problem, the distance from the nearer end of the strip to the axis of rotation is 0, right? The strip extends all the way to the axis of rotation. So little r is 0, and big R is this distance. Little r is equal to 0 because the strip extends all the way to the axis of rotation. In order to figure out what the big R is, I need to characterize this point. Since I'm along the graph, y equals x plus 1, this is x comma x plus 1. So little r is 0, and big R is x plus 1 minus 0, is just x plus 1. the y value at this point minus the y value on the axis of rotation, which is 0. So then dv is pi times cap r squared minus little r squared, in this case, times dx, because my thickness is a dx thickness, which is pi times x plus 1 squared minus 0 squared dx, which is just pi times x plus 1 squared dx. And then v is the integral of dv taken from the smallest x value in the region to the largest x value in the region. So that's from 0 to 7. So that's going to be the integral from 0 to 7 of pi times x plus 1 squared dx. Well, if I rotate just this strip about the line x equals 0, about the line y equals 0, the x-axis, I will get a disk. It won't have any hole missing in the middle. My little r is 0. So that's why they call it the disk/washer method. It's not a washer, it's a disk. In other words, it's a washer where the radius of the inside is 0. Yeah, so it's not the area of the strip we're looking at. It's the area of the cross-section of the disk that's generated by rotating the strip. From here, things are fairly straightforward. You pop out the pi, you integrate 0 to 7, the square of this, which is x squared plus 2x plus 1. And so that's going to be pi times x cubed over 3 plus 2x squared over 2 plus x evaluated from 0 to 7. And then the last few steps here aren't particularly entertaining. The 2's, I suppose, can cancel. When you plug in 0, you're going to get 0 everywhere. So this will be pi times 7 cubed over 3 plus 49 plus 7. And then you can simplify that if you want. I don't want to burn too much class time on arithmetic. I'm not sure what 7 cubed is off the top of my head. I think it's like 343 or something, but I don't know. So this would be your answer, and you would want to clean that up. You would want to write that as a single fraction. But the real money here is in the setup, right? It's important that we understand how to set up these integrals. I know the integrals themselves are not very hard because we don't have a whole lot of integration techniques at this point. They'll all be like power rule integrals or stuff that you know from Calc 1, U sub, that sort of thing. Any questions about the setup here? How I got that dv was pi times x plus 1 squared dx? That's the real work. Little r here is 0 because little r is always the distance from the nearer end of the strip to the axis of rotation. And here the strip extends all the way to touching the axis of rotation. So there is no gap between the end of my strip and the axis of rotation. So the distance between the bottom of the strip and the axis of rotation is 0 because the bottom of the strip is sitting right on the axis of rotation. So in other words, it's coming from the picture. And if there's something you'll notice about these problems, it's that drawing the picture nice and big so you've got room to get in there and label shit is pretty much always the key. No, you wouldn't have to include the little r, right? If you want to, you can memorize different formulas for the disk method and the washer method separately. But I do it this way because I want to force you to memorize the smallest number of things, right? So the formula that I gave you here, dv equals pi times cap r squared minus little r squared, that is kind of the nicest, smallest, simplest thing you can memorize that will work for all of these problems. So that's my recommendation. Otherwise, you're going to have to identify, oh, am I using the disk or am I using a washer? And think of the two formulas separately. And I don't encourage that. So it's up to you. It's kind of a matter of taste. And I invite you to Google around. perspectives and techniques that I present here are very rarely the only perspectives or techniques that are legitimate. They're just the ones that I think you will find most palatable. So if you would prefer to do something else, I encourage you to explore and see what other things might work for you. But what I'm presenting here is what I think will work the best for the most number of people, which means usually memorizing the fewest numbers of formulas. There are many problems where you will need the little r, right? Like the last two problems we did, little r was not 0, and so you do need that. So if you're going to separately memorize formulas for the disks and the washers, just make sure you can identify which situation you're in. Yeah, me too. I hate memorizing formulas. That's the bane of the math teacher's world. Like, who wants to memorize a bunch of stuff? We'd all rather just think through it. But that's not always true. Sometimes it's easier to have some formulas that you can lean on if you're feeling overwhelmed, especially at first. So don't panic if that's the case. I am going to conclude class today with a list of formulas for you. So don't panic. But I would like to now go ahead and introduce the method of cylindrical shells. So are there any other questions on this particular example? Okay. So then, my favorite way to introduce cylindrical shells is to present a problem that requires it. So, why would we have more methods than we need? So if we're going to try to motivate the use of a new method, we should see why it's necessary. So suppose I wanted to do the same sort of thing. So this is intro to 6.3, volumes via the cylindrical shells method. I'm going to look at the sine of x squared, which looks like this. This turns out is the square root of pi. So here's the graph, y equals sine of x squared. And so I've got a little region there, and I'm going to rotate that region. I have to remember. Rotate that region, I think about the y-axis, and see what might be challenging. Where did my shit go? Yeah, all right. About the y-axis, yeah. So I want to take that region, rotate it around this axis, and see if I can find the volume of the resulting solid. If I wanted to do this using the method of disks and washers, would my strip be oriented horizontally or vertically? Right, horizontally. So let's pretend like I was going to do that. Can we find this volume via the method of disks and washers? Well, if I jump into this with the disk washer method, I'm going to draw my strip like this. It would have a dy thickness, which means I would need to give this distance and this distance as functions of y. What's hard about doing that is that this function sine of x squared, if I'm looking at just some generic y value here, I cannot characterize both of these points in terms of y. It can't be done because this function isn't one-to-one. I can't solve this nicely for x. So the points, I call them P2 and P1. The points P1 and P2 cannot be expressed in terms of y, because y equals the sine of x squared is not a one-to-one function. Think about what we were doing when we took the points on those curves that were originally given in terms of x and expressed them in terms of y. We were really finding the inverse function to do that, right? We went from x equals y squared to y equals the square root of x, or from y equals ln of x to x equals e to the y. In each of those cases, what we were really doing is writing, we were going from something like, so we can't go from, so i.e., or that is, right? It's a Latin abbreviation for that is, can't go from x comma f of x to f inverse of y comma y, because f inverse does not exist. Because f isn't 1 to 1. So the only functions that have inverses are one-to-one functions. This function, obviously not a one-to-one function, right? Fails the horizontal line test. Which means I can't recharacterize a point on the graph, which I would normally write as x comma f of x, what we were talking about earlier. Normally, I could rewrite this point like this, where like I've got x comma ln x. Okay, that's the same as e to the y comma y. The only reason I can get away with that shit on the example with the ln x graph is because ln x is a one-to-one function. Otherwise, I would run into trouble there, because what would I use here? The inverse of ln x is e to the x. So if I want to write f inverse of y, that would be e to the y. But here, sine of x squared doesn't have an inverse. He's not one-to-one. You could restrict his domain to make him one-to-one, but that's necessarily going to mean chopping the picture here and throwing away half the graph, which means important shit that I need for my volume problem are going to get thrown away. So in other words, setting things up here is hard. More than hard, it's impossible. We couldn't possibly set this up using the disk washer method because I could never write little r and big R as functions of y. And I would need to write them as functions of y because my integral is going to be a dy integral because my strip is a dy thickness. In other words, a new method is required. Yep. Yeah, that's true. If the graph fails the horizontal line test, and there's no way to like get around it. Like if these were two different curves and I had different formulas for each of them, then I could get around this. Or if there was some convenient way to write these points as just in terms of y, then I could get around it. But here there isn't any such thing because they're coming from a single curve that fails the horizontal line test. Yeah. Right. So the question becomes, all right, fuck the horizontal strip. What happens if I try to do all these things the same, but I draw my strip in vertically at the start? What's going to happen is the shape of your little differential solid is going to change. It's not going to be a disk or a washer anymore. It's going to be something else. So you're going to have a different formula for dV because the geometry of the little differential solid is going to be a different shape. But everything else is going to flow the same. It's going to work out beautifully. So let's see how it goes. What happens? Can we draw the strip vertically, which would be parallel to the axis of rotation? and kind of follow our nose? Let's see. So here's that same curve. Here's my axis of rotation. Wait, what was my axis of rotation? It was the y-axis, right? And now I'm going to draw my strip in parallel to the axis of rotation. Now the strip's thickness is a dx thickness, which saves me from having to find an inverse for this function, which I know doesn't exist, right? Here, y is still the sine of x squared. So this point I can characterize conveniently in terms of my important variable, which is x. This is x comma sine of x squared. But if you rotate that strip about this axis, if you just rotate the strip, which normally we would have generating our differential disk or washer, here it's going to generate a different shape. If I rotate just that strip about this axis, you imagine it, I'm going to get a little cylinder. It's actually a cylindrical shell. It's got a very thin wall thickness. The thickness of the wall is the thickness of the strip that I'm rotating. And it's got a little height. Do you see how rotating that strip would generate a solid shape like this? Like here is the strip. And as this strip spins around this axis, you generate this kind of shape. Think about taking a big cylinder and then boring out the middle of it, right? So you take a big cylinder like this that has the dimensions of the outer dimensions here, and then you take a drill bit that's just a little bit smaller than that cylinder and you ream it through. You'd be left with something like this. So take a second, make sure you're seeing how this shaped solid is what you get by rotating this strip about an axis parallel to the strip. Can you see it? Is there anything that feels weird that we'd like to ask about? Normally at this point, I'm able to stand up and wave a few things at you in front of you in the classroom. Here, I don't really have that opportunity. Let me come out of the screen share here. Well, probably actually easier to do it like this. So share with you some pictures, maybe a GIF. Find something with some animation that's usually really helpful. Man, this is a little disappointing. Well, what do we have up here? One of these looked okay. Is this animated? Okay. So let's watch this. Let's see if he does a decent job with this. He's going to take just one of these little guys And then he's going to imagine rotating that around the y-axis. Do you see it? It's creating this cylindrical shell shape. Does that help? So we take the region. He partitions the region instead of, so we think of this region as being made up of infinitely many of these very, very thin strips. And then each of these very, very thin strips rotates, just like this green thing is here, to create a little cylindrical shell, a little shell of a cylinder. Yeah, the drawing skills here are definitely put to the test. Mine are also, and you'll notice my art is bad. I will not hold your art to high standards, but maybe if you're having a tricky time visualizing the stuff, I'll paste this into the chat. So for animations to help visualize the cylindrical shells strips. See here. All right. I would also bet that that site has some good stuff for the other method too. This is actually a really nice site. And there are other examples here. We can look at one or two more maybe. So here we're taking the region, we're chopping it up. That gives us a bunch of little strips. We're going to grab just one of those strips and imagine rotating it, and we'll get a little shell. And then we can.
Why do we only get one strip? Are we going to calculate all the strips?
Well, that's what the integral does, right? So your dv is what you get from one little dx thickness strip. And then the integral adds up the volumes of all those little shells. And that's what gives you the volume of the whole thing. So we look at one strip to get a formula.
So that's one strip that's going 360 around the y-axis.
Right. And so we get a formula for the strip that's located at this generic point x. And then and that adds up the volumes that we get from all the little strips. So
what kind of shape would this be if this is like a parabola and we flip it around on each strip?
Let's watch. So here he's going to do that for each of the partitions.
And this is what the integral does.
Mm-hmm. So you can think of these nested cylindrical shells as being the Riemann sum for the integral that we calculate. So there's shell 1, shell 2, shell 3. And the overall shape here is going to be a cone for this one.
That looks, yeah.
Right? It's very neat. The more of these you watch and the more you play with these things, I think the easier it will be for you to see what's going on. So here he's doing it without the strips. He's just rotating that region, and he's going to give us a nice picture of the solid. And then if we want to see what happens with the strips for that particular solid, that was this. And the idea is that if we're able to come up with a formula for what happens with one of the shells, we can integrate that to find what happens with all of the shells. And all of the shells is the whole solid. So that will be the whole volume. So take a look in the chat. I pasted a link to this website. And I think if you play around with those animations, they'll help you develop your intuition a little bit more.
You didn't paste the website.
Yeah, have a look in the chat here for Zoom. I'm looking. 42. Oh shit, I sent it just to Ryan. Sorry. Here, let me paste this to everybody. There you go. Yeah, so now it's at timestamp 12:45. You'll see the link to the website. You can play around with those different things. And I hope that will help you develop the intuition. For now, I want to focus on the skill building. So let's return to the problem we were working at. The question I need to answer in order to proceed from here is, how do I find a formula for dV? So the volume of this one shell is dV. Since my strip is dx thickness, that means I need to come up with a formula for dV in terms of x so that I can integrate it, because I'm going to need to integrate dx. The way we do that is by, I imagine coming in here with some very sharp scissors, and I cut this shell right here. And then I unroll. So that's going to give me a little rectangular prism. So like if you have, imagine you have a soup can with the top and bottom removed. If you cut up the sidewall, you can then unroll the can and you'll get something like this, where the thickness is very, very thin. That's our dx thickness. And it has two other dimensions. It has like a length and a height. So now instead of finding little r and big R, I need to find these things. That height is this height. It's the height of the strip. What is this dimension? What is the length of this very, very thin rectangular prism?
Is that the circumference?
Yeah, it's the circumference of the shell. So this is,
Because you said you're unrolling it.
right, exactly. So this is 2 pi times the radius, where the radius is the radius of the cylindrical shell. Right? Circumference is always 2 pi r, 2 pi times the radius. So I cut and unroll my cylindrical shell into this rectangular prism. Its dimensions will be the differential thickness, which for this was dx, times the height, which is the height of the shell, times 2 pi r, where r is the radius of the shell. And then you come back to this picture and you find h and you find r. We need to express them as functions of x, because my goal here is to do a dx integral. So thinking about those animations we were looking at, what distance in the picture here is the radius? Well, it's the distance from the strip to the axis of rotation. Right? Imagine rotating the strip. Look back at those animations. The radius that we're getting for the given shell is the distance from that strip to the axis of rotation. All right, watch this shell. If you look straight down from above, you're going to see a green circle. And the radius of that green circle is the distance from the middle of the circle to its edge, which is the distance from the axis of rotation to the strip. So that's this distance, which is just x, because I'm rotating about the y-axis. And the height of my cylindrical shell is coming from the height of the strip, which is just this y value. So that's the length of the strip. It's, in this case, the sine of x squared. So the first time I was introduced to this, my Calc 2 professor didn't call this the method of cylindrical shells. He called it the onion method because, you know, you can see these things kind of look like onions, right? It's got layers, it's concentric layers. And he said, just like chopping an onion makes you cry, using this method will make you cry. So it's okay if this stuff feels weird and challenging right now, but it's important that you're able to follow each little bit as we go along, and then you can rewatch the videos, you work the problems, and it'll start to make more and more sense as you go. Do we see why H and R came out the way they did? Why the radius of this shell is this horizontal distance, and why the height of this shell is the height of that strip?
Yeah, that makes sense.
Okay. So do we see why the height of the strip is sine of x squared? Because the y value down here at the bottom of the strip, the point down here at
I have a question though.
x comma 0, because it's along the y-axis. So it's this y value minus this y value for the height, and this horizontal distance, which is just x for the radius.
Does it account for the thickness?
No, that's the thing. Yeah, so you're getting at one of these kind of funny things that happens as you pass from the Riemann sum to the integral thing. The thickness of the strip being dx means it's really infinitely thin. So I don't have to worry about whether I'm looking at the distance from the left side of the strip or the right side of the strip to the axis of rotation. Sorry, this is one of the kitty cats, and he's
What's his name?
dancing for us. His name is Nova. He's been called a burnt marshmallow. Anyway, so coming back to our DV, I can cut and unroll this strip into this prism. The volume of this prism is going to be length times width times height. So dV is 2 pi r, that's your length, times h, that's your height, times dx, because that's your thickness. And for this particular problem, that's 2 pi times my radius was x. My height is the sine of x squared, and dx is just dx. Good so far? All right, questions so far?
Why did you use that formula?
The 2 pi rh dx?
Mm-hmm.
Well, because the length of this thing is 2 pi r, it's the circumference of this thing. The height of this thing is h, and the thickness is dx. So the way you find the volume of a box, right, is length times width times height. The length is 2 pi r, the width is dx, and the height is h. So length times width times height is 2 pi r h dx. I always like to write the dx at the end because I know I'm going to write an integral, and we always put the dx at the end.
Okay.
What happens if the radius isn't as simple as x? Well, then you use whatever it is. If I was rotating, instead of rotating about the y-axis, if I was rotating about the vertical line x equals -2, then my radius would be the distance from x to -2, which would be 2 plus x. So in any of those cases, we draw this picture, and we think about r and h in terms of distances, and then we come up with the formulas. So we'll look at examples like that. I'm going to return to that ln(x) example and set that up for you using the cylindrical shells method, and that'll be our last little example here. Wouldn't the distance from the strip to the axis of rotation, well, you would find the distance? Right, yeah. What Morgan said is a good response to Lucas's question. You would find the distance from the strip to the axis of rotation, whatever that is, and you use that for your radius. So let's go ahead and write down the integral. I have dv, 2 pi, god damn it. I don't know why, my phone's just blowing up today. All right. So v is the integral of dv. And since I'm doing a dx integral, my strip's thickness was a dx thickness. That means my bounds need to be x values. So my region begins over here at x equals 0, and it ends over here at x equals the square root of pi. So I'll be integrating from 0 to the square root of pi. And the thing I'm going to be integrating is dv. So that's the integral from 0 to square root pi, 2 pi x sine of x squared dx. Now the 2 pi is a constant, it'll pop out. I get integral 0 to root pi x times sine of x squared dx. How do we do that integral?
Using U substitution.
Yeah, we'll use a little u sub there, right? A little substitution. What am I going to sub for? Good, yeah, x squared. because that's the inside of my sine function. If it was just sine of x or sine of z, I know what to do with that. And if I let z be x squared, then dz is going to be 2x dx. So that'll take care of my x. So I'm going to let z be x squared. dz then is 2x dx. I also need to change my bounds. When x is equal to 0, z is equal to 0 squared, which is also 0. When x is equal to the square root of pi, z is equal to the square root of pi squared, which is just pi. So this substitution makes my integral much nicer. And I end up with the integral, 2 pi, sorry, times the integral from 0 to pi of sine z, because I have the sine of x squared, and z is x squared. And then I've got this x dx. Well, x times dx, that's 1/2 dz. Because dz is 2x dx. Divide both sides by 2. So there's a 1/2 dz here, and that's that substitution done. Now that 1/2 will pop out and cancel with the 2 in the front, so this is pi times the integral from 0 to pi sine of z dz, which is not a hard integral. An antiderivative for the sine of z is the negative cosine of z. So this is pi times negative cos z, evaluated from 0 to pi. The cosine of pi is -1, and the cosine of 0 is +1. So this is pi times -1 minus, oh wait, I need to do this very carefully. I'm sorry, being sloppy. This is pi times negative cos of pi, which is -1, minus negative cos of 0, which is +1. So that's what that evaluation looks like if we're careful with our minus signs. Which is 2 pi, right? This is 1 plus 1 is 2 pi. Nope, because we changed our bounds. Remember, this is why in Calc 2 we require that every time you make a substitution, you change your bounds. So you can just evaluate between those new bounds. As long as you change your bounds when you make your substitution, you never need to go back to the old variable, and you shouldn't. You should always just change the bounds along with the substitution and evaluate the new bounds. So if you go back to the videos from last Wednesday, I talked about this, I think, at a little bit of length, the importance and value of doing the coordinate transform in earnest. So that's the volume of the cylinder. Yep, the volume of, well, no, that's the volume of the whole solid. The volume of the cylinder, this particular cylinder that you get by spinning this particular strip around, where that strip is located at the generic point x, is 2 pi x times sine of x squared dx. The volume of the whole solid is 2 pi. Okay. So I know that we've gone over, I think, a little bit our time here, but I do very quickly want to show you the setup for that LNX problem using cylindrical shells. So if you'll bear with me for just 1 second longer, let's return to that problem. This problem is actually much nicer to set up using this method of cylindrical shells, and it'll let us see what happens when the radius isn't just x. So because I want to use this new method, the cylindrical shell method, I draw my strip parallel to the axis of rotation. I'm along the curve y equals ln x, which means this point is x comma ln x. So what I need is this radius and this height. The radius here, from here to here, is just x, right? Because this strip is always located at just a generic x value. This distance over here is 1. So this is x plus 1. And that's how we handle this situation where the radius is not just x. You look at the picture and you sort out whatever the distance from the axis of rotation to your strip is. This distance here, from the line -1 to 0, that distance is 1. And this distance here is x. So the radius overall is 1 plus x, or x plus 1. And then my height is just ln of x. No stress, no stress. So if you gotta go, you gotta go. This is ln x. So the last thing I'll do here is write dv is 2 pi r h dx, which is 2 pi times x plus 1 times the ln of x dx, which means that v would be the integral of dv taken from x equals 1 to x equals e, 2 pi times x plus 1 times the ln of x times dx. So the setup here much, much easier when you use the cylindrical shell method. The catch is we don't yet know how to do this integral. This integral cannot be done by u sub. This integral cannot be done with the power rule. So we're going to have to develop some new methods, and that's what we do starting in chapter 7. So this integral requires a method called integration by parts, and that's what we're going to start talking about next week. On Friday, I will work through more of these cylindrical shells problems with you guys and try to get you a little more comfy with the method. If you haven't typed anything in the chat yet today, please go ahead and type the word here so I have a reasonable attendance log, and then you are welcome to go. If you want to talk to me after this, you want to look at any problems or have questions in general, I will be holding an office hour starting in just a few seconds. Any last minute stuff before we end class today?
So you can use that method for anything, like if you want to find any volumes.
The cylindrical shells method works in some cases where the disk washer method doesn't, and the disk washer method works in some cases where the cylindrical shell method doesn't. For many problems, you could use either. And if the curves that define the region you're rotating are 1-to-1, then you can always use either. But if the curves are not 1-to-1, then sometimes you will be forced to use one or the other. The big difference between the two is whether you draw your strip parallel or perpendicular to the axis of rotation. And then the question is, can you get the distances you need as functions of the variables you need? So it's kind of something you have to do ad hoc. You have to look at the region and ask, can I find the distances that would be required by the one method as a function of x or as a function of y, depending on what the situation calls for. If you can, then you can use that method. If you can't, then you can't use that method. And it's something that you kind of just have to play around with. So if you're having a very hard time setting it up one way, try using the other method. That's as much strong advice as I think I can give there, is that you'll just have to play with it. But on Friday, we'll examples of both types, and we'll play around and I'll compare the two for you. Yeah, I heard that someone was asking something there. Yeah.
No, I said thank you.
Oh yeah, okay. All right, I'm going to go ahead and end this meeting in case I've got people waiting for me in the office hour from my other classes. If you want to talk more, just go ahead and exit this meeting and join the office hour meeting. All right, thank you guys for coming. I hope if I don't see you that you have a nice rest of your day, and I'll see you on Friday.